So our next talk is Post-Quantum Security Models for Authenticated Encryption by Vladimir Soukharev, myself, and Srinath Seshadri, and Vladimir Soukharev will be giving the talk.
Hello, everyone. So this work was actually inspired by our research area. Basically, we're doing post-quantum cryptography that is based on isogenies between supersingular elliptic curves. And once we wanted to build an authenticated encryption scheme that is based on isogenies, we came across the fact that there's no fundamentals in the post-quantum world at this point for doing authenticated encryption. So we had to formalize that and work on some proofs. And that ended up being a paper itself. So I'll talk about the construction, and then I'll present our actual isogeny-based scheme. So basically, Belair and Umpremper in 2008 have shown that in order to obtain a secure, and secure we mean indistinguishable under chosen ciphertext attack, authenticated encryption construction, we only need indistinguishable under chosen plaintext attack encryption scheme, strongly unforgeable chosen message attack under signature scheme or a MAC scheme, and we need to use encrypt then MAC technique. So the question that naturally arises is how to do this for a quantum resistant scheme. And so we'll adopt the definitions for this scenario with the quantum adversary, and we'll show how to obtain quantum resistant authenticated encryption schemes. Okay, so we need to look at some of the definitions. The problem is that the classical definitions don't quite directly transfer into post-quantum world. So, and Boone and Zandri have looked into that. So in order to define a indistinguishable under a quantum chosen message attack scheme to show its security, we need the following. So we have the adversary who does the querying, and we have the standard bit B, which has been picked by the challenger, and so the encryption happens of the challenge message classically this way, but then the actual encryption queries are done quantumly. So once we feed in a message in quantum superposition, we get encryption. It was the corresponding quantum superposition, and so the goal of the adversary is again to guess the bit B of the challenge message. And we cannot use the natural extension of the indistinguishable chosen plaintext attack in a classical world definition. And Boone and Zandri actually show that if we do just let purely quantum queries, we can show that no single scheme satisfies this. And so because allowing fully unrestricted quantum queries makes the definition just way too powerful. All right, so next definition is indistinguishability under quantum ciphertext attack. And it starts off the same, and then again we have the decryption queries, and the decryption happens again once we fit in a ciphertext in quantum superposition. We get a decryption in quantum superposition, except if one of the messages here was one of our challenge messages, then we don't return the actual decryption of it, of course. And again, we want to guess the right bit B. Okay, so strongly unforgeable under quantum chosen message attack for our signature scheme or a MAC scheme. Again, we have a key generation procedure, and then adversary makes a polynomial Q. Q is the number of message queries, and obtains the encryption of it. So this happens again in quantum superposition, messages, signatures, or tags. And adversary is required to produce Q plus 1 message signature pairs. So the major difference from the classical point of view is that in classical point of view, we said, here, given Q queries, message queries, give us one more. In quantum, we say, given Q, give us Q plus 1. And one of the reasons for that is that, for instance, we can actually have the same query which will produce different signatures because depending on how we measure it. So we cannot directly use the classical definition. And again, as I mentioned, instead of asking new pair, we just say Q plus 1 valid pairs. All right, now we have the weak version. So a signature is weakly unforgeable under quantum chosen message attack if it satisfies the same definition except that we require the Q plus 1 message signature pairs to have distinct messages. So in the strong version, the messages don't have to be distinct as long as the signatures verify. All right, so Belair and Prapri make use of the definitions for the classical cryptographic notions. Bonet and Zandri show that we need to sort of do an upgrade of definitions to be able to talk about quantum adversary scenario. And in order to be able to prove the main results, following the approach that's analogous to Belair and Prapri, and more, we'll need more definitions because Bonet and Zandri, although they start off showing some nice definitions, we need a few more to complete the idea. And then we're going to use, but the ideas are going to be very similar to what they use. All right, so one of the definitions that we need is for our encryption scheme, in order for it to satisfy the integrity of ciphertext under quantum attack, we need to make sure that adversary is not able to win this game. So the challenger is going to pick a random key K, and he does Q queries. Again, he can do that in superposition. So message in superposition gets encryption in superposition. And he can also obtain the decryptions. Again, he feeds in ciphertext in superposition, obtains decryptions in superposition, except that we're not allowed to take the challenge ones. And so he's required to produce Q+1 message ciphertext pairs. And we have the plaintext version of it, which is basically the same idea, but except the message ciphertext pairs have to be distinct. All right, so what are the results in summary of Belair and Prapri is that we have weakly unforgeable MAC actually implies that our authenticated encryption scheme is going to have integrity of plaintext, strongly unforgeable, integrity of ciphertext, indistinguishable under chosen plaintext stack encryption scheme implies that we get indistinguishable under chosen plaintext attacks authenticated encryption scheme, integrity of ciphertext, and indistinguishability under chosen plaintext attack gives us indistinguishable under chosen ciphertext attack authenticated encryption scheme. So the major result is if we have indistinguishable chosen plaintext attack encryption scheme and strongly unforgeable MAC or signature scheme, we obtain indistinguishable under chosen ciphertext attack authenticated encryption scheme. So what we do is we pretty much get exactly the same picture except with all those Qs in there. So we had to go into the proofs, make sure that all the parts work, and if the parts that did not work, we had to fix them. And very nicely, we've been able to prove that actually the same result holds for the quantum world, changing the proofs inside and making things that didn't work before, making them work. So our, again, main result is if it's undistinguishable in quantum chosen plaintext stack and strongly unforgeable under quantum chosen message stack, we have the indistinguishable under quantum chosen ciphertext stack authenticated encryption scheme. And of course, we use the definitions that are specific for post-quantum world, which are like extensions of the classical definitions. Okay, and here's just an example of some of the theorem statements. This is just show an example, and each one of those statements has a similar theorem and a huge, like usually sometimes shorter, sometimes longer proof to them. So if we have strongly unforgeable quantum chosen message stack MAC, and it implies integrity of quantum ciphertext. Similar ideas here. And of course, the main theorem is that we get indistinguishable quantum chosen ciphertext attack authenticated encryption scheme. And the basic idea is that combining all the previous results, if we are MAC or signature scheme strongly unforgeable quantum chosen message stack, we get that authenticated encryption scheme has integrity of quantum ciphertext. Now our encryption scheme is indistinguishable under quantum chosen plaintext attack. Authenticated encryption scheme has the same property then. And finally, authenticated encryption scheme, because now it has integrity of ciphertext under quantum attack and indistinguishable under quantum chosen plaintext attack, we get that's indistinguishable under quantum ciphertext attack. All right. Next thing is, well, we need quantum resistant signatures, and we know that most classical signature schemes are insecure in a quantum model, and we can actually apply a transformation by Bonet and Zandri that they did, their work they did in 2013, to some of the existing signature schemes. But there are some restrictions of what kind of signature schemes can be used for that transformation. So in order to be able to make a classical signature scheme quantum resistant, we need it to be secure classically, of course, and it has to classically reduce to a quantum resistant problem. So if these two properties are satisfied using Bonet and Zandri's transformation, we can actually obtain quantum resistant signature scheme. And this is how this transformation looks. So basically, we need to grab our classical signature scheme, which of course has the key generation, signing, and verification oracles. And we're going to define the new signature scheme in this way, where key generation is exactly the same. Signing, so here we need this family of pairwise independent functions mapping messages to randomness if the original scheme had one. So we need to take that, which basically, it's basically mapping messages to randomness here. We need this random R. So taking the message, mapping it to randomness, taking R and message, hashing it together. Our signature is going to be basically using the same secret key. We're signing H and S here. And our output is going to be R and this sigma here. Verification, well, fairly simple. We do the hashing first with this random R and verify that it actually satisfies. And the result that Bonet and Zandri show is that if our classical scheme was secure, strongly unforgeable chosen message attack against the classical chosen message attack by quantum adversary, then the transformation scheme S is strongly unforgeable quantum chosen message attack. All right, so now how does the authenticated encryption scheme looks? Basically setup, so we choose parameters for the underlying encryption and signature schemes. Then we take a hash function, which is secure with secure parameter k. We need the family of pairwise independent functions mapping messages to randomness. Key generation, Alice needs to choose her private key parameters for the encryption and signature schemes. If needed, she's going to produce and publish the corresponding public keys. Bob is going to do exactly the same thing symmetrically. Okay, now suppose Bob wants to send a message to Alice. So he takes the message and using the common encryption key E that they have, or they've shared or somehow exchanged with Alice, encrypt the message under the underlying symmetric key encryption scheme in this way. Then he's going to select the queue at random, map the message to randomness, compute this value H using H in his private key, signing. Bob computes the authentication tag, and this is the ciphertext. So here's the decryption. Decryption happens in a similar way, and so they use common encryption key to decrypt it. So he first verifies that it matches, and then decrypts it if so. All right, now we're gonna move to isogeny-based scheme that we came up with. So, and we'll do a very quick introduction to elliptic curves and isogenies. So, what are elliptic curves? Basically, you have a finite field, and I mean here we're going to use a Weierstrass equation. So it's basically a set of points x, y in our finite field that satisfy this equation plus the point infinity, which serves an identity, forms a group. Now, they have a nice group law, so given 2 points, we can add them nicely to obtain a third point. And isogenies. So what are isogenies? So we let E and E prime to be an elliptic curve over some finite field F. An isogeny is basically between two elliptic curves is a non-constant algebraic morphism, which is a group homomorphism, and it satisfies that identity gets mapped to identity. And degree of an isogeny is its degree is an algebraic map. And the endomorphism ring, end of E, this is a set of all the isogenies that go from E to itself. Now, we said endomorphism ring, it is a ring under where the addition happens pointwise and multiplication operation is the composition of the isogenies. Just a quick, simple example what isogenies look like. Isogeny can be like as simple as a multiplication by n map. And here's an explicit example, multiplication by 2 map. Now, the degree of the isogeny can usually be obtained here. So C multiplication by 2 map, its degree is 4. All right. So why use isogenies? Well, finite isogeny between given supersingular elliptic curves over a finite field is believed to be a computationally feasible problem for quantum computers. It's basically one of the sort of major 5 areas where in the post-quantum cryptography. Now, together with my supervisor and Andrew Childs in 2011, we have shown that the isogenies over ordinary elliptic curves cannot be used as cryptographic parameters for quantum-resistant protocols. We basically show that there is a sub-exponential attack, but the same attack is unapplicable to supersingular elliptic curves. Now, Zhao and DeFeo in 2011 have constructed quantum-resistant key exchange protocols that is based on isogeny between supersingular elliptic curves. And in 2014, we have constructed a quantum-resistant undeniable signature protocol that is also based on isogenies between supersingular elliptic curves. And so we're continuing in that direction. So we present now an example of quantum-resistant authenticated encryption scheme, which is based on elliptic curve isogenies. And for our signature or MAC scheme component, we make use of the idea that was originally presented by Santian and Wang. Now, just a quick note about their work. Their work claimed more than they've actually have really proven, but using Bonnet and Zandri's construction, we actually do bring it to the level of security that they claimed. Now, the key exchange component is based on David Zhao's and DeFeo's protocol that they've presented in 2011. Okay, so how does the setup go? Basically generate these primes and these 2 primes as well, which are of the following form. So the LA and LB are fairly small primes, could be like 2, 3, 5s. And then we make the degree corresponding depending on the exponent here. So we get these 2 primes, and we take the elliptic curve equation, and we define them over the 2 finite fields. Now for supersingular elliptic curves, it's enough to go to degree 2 extension. Now, we know that this is this subgroup of the elliptic curve has 2 generators. So this one generates this one. These 2 generate this subgroup. We do the same thing symmetrically with the P prime version. And we need some hash functions that are secure. Now, I know this is a lot of writing. I'll show you on the next slide a nice picture of it. So basically what Alice does is she generates these 2 private parameters, just integers, mod LA to the power of EA, and also a second set for the prime version. And these ones are used together with generators to find our image curve EA. Now this is the secret part. And once we know these 2 or the kernel or any of those 2, we can equivalently show that they reduce to the same part. Now the public part is our image curve EA. Same thing for the prime version. So, and then we also need to define our isogeny on the basis point for the Bob's parameters here. Bob does the same thing symmetrically. All right, so what is really happening? So we have our first curve starting here, E, and our second curve, E prime. Things are happening somewhat simultaneously here. So these PA, QA, PB, QB are all public parameters. Their images under the isogenies are also public. So Alice generates this MA-NA, uses that as the kernel. Now kernel, isogeny, they're all interchangeable. If we know one, we know the other. So she calculates this isogeny mapping to EA. So this is secret part, this is public, this is public. Bob does the same thing. Now Bob takes Alice's image, Alice's, like the image points of PB, QB, his private parameters, and maps this way from EA to EBA. Alice does the same thing symmetrically, maps to here, and these 2 curves are going to match up. Although the endomorphism ring is non-commutative, these things do commute. Same thing is happening for this one. So basically, these are going to be the 2 parts that we use for encryption scheme and message authentication scheme, or a signature scheme part. Okay, basically, so now saying that in words, so we compute the ciphertext, we compute their common elliptic curve over P, which is EAB, and we take the J invariant and use that as the key to encrypt the message, and then we use the hash, and then Bob is going to compute the authentication tag using Santian and Wang's idea. And their idea is basically that we take, their signing is we take the message and we use the J invariant here as our private key. We concatenate them and take a hash of, and that serves as a signature scheme. And so the ciphertext is of this format. Decryption, well, happens in the same idea as shown before. We need the hash, the J invariant corresponding to E over the P prime, the EAB, the common curve to them. Check, make sure that it actually authentication tag verifies. If it does, decrypt the message. All right, so just a few notes on the scheme, the ciphertext. So we're going to talk about the overhead. So the ciphertext which Bob sends to Alice consists of a triplet, the C, R, and sigma, where C is the underlying ciphertext, R is the k-bit nonce, and sigma is the signature tag. In the case where the verification function in the signature scheme involves independent deriving the value of sigma, we can actually hash sigma down to k bits as well, and isogenes are friendly with hashing. For a security level of L bits, the minimum value of k required for collision resistance is 2 times L bits in the quantum setting, and then the per message communication overhead for the scheme is 4 times L bits. In the case where the signature tag can be hashed, and in isogenes we can do that, and if it cannot be hashed, then it's 2L plus the size of the signature or the message tag. And so in the former case, the per message communication overhead is always the same, independent of which component schemes are actually used. All right, and just comparing the public key overhead. So the public key sizes that apply to the authenticated encryption scheme come from a key exchange section. So we aim for 128-bit security here, it's quantum security. And note that the strong designated verified signature scheme of the Santian and Wang idea require a two-way transmission of public keys even if the encrypted communication is one-way, whereas standard signature schemes require two-way transmission of public keys only for a two-way communication. And here we compared to some other post-quantum secure schemes, and notice that the isogeny-based ones have their size of the public key is the smallest. Okay, so conclusion, some future work. So we proposed a security model for authenticated encryption against fully quantum adversaries based on classical security model of Biller and Amprompery. We apply the Boone and Zanders framework for modeling quantum adversaries. We provide concrete examples of authenticated encryption schemes satisfying our security model along with the estimates of overhead costs for such schemes. And so some of the next steps there is that notice that our scheme is standard uses the standard ideas that have been used classically before, and it would require authentication of public keys. Now, maybe you're looking for something that would be post-quantum secure, but would not need the authenticated public keys, something like of the ideas using ESSR, but except doing the post-quantum version of it. And also, our authenticated encryption scheme is a composition of encryption scheme and a signature or a MAC scheme. Now, maybe it would be one of the directions to follow is to produce something that's post-quantum secure but atomic, like a one-step protocol, something like an idea of sign encryption, AES-GSM, or something along these lines. Okay, thank you.
Any questions?
You called your security model post-quantum in the beginning, while Bonnet and Sandry explicitly distinguish between post-quantum and quantum security models and actually say the Q-and model is a quantum security model. The assumptions are much stronger than what we consider in a post-quantum setting. Is there some motivation behind this?
Well, we basically thought that realistically, if we have a quantum adversary, then we want to be able to withstand that quantum adversary, right?
So then you assume that every quantum adversary suddenly can force the users to behave quantumly? Because that's what you require if you assume superposition assess?
Well, we are making the model more strong. So we're saying that we have this oracle which can actually do the quantum queries. So the users are still doing it classically, but the oracle is able to respond quantumly.
But what's the oracle modeling?
Sorry?
What is the oracle modeling in this model?
Oracle? Well, it's just, basically like a black box where you fit a quantum.
Yeah, but it models a user.
Well, in case even if the users have a quantum access, say we have quantum computers around, right? They can technically respond quantum. They can communicate classically with each other, but they can possibly still respond quantumly. Say we put our classical scheme on a quantum computer, then that would be possible, right?
Okay, but that's exactly why Bonnet and Sandry make this distinction between quantum security and post-quantum security. So actually, you were proving or developing a quantum security model, right? Not
Well, technically, yes, it's like a quantum security, but I mean, the idea is that, I guess, why it still satisfies the post-quantum part is because we can do it classically regardless.
Includes, yeah. Thank you.
Questions? One second, please.
On the slide, when you have the comparison, could you precise which schemes that you have considered for code-based and multivariate?
Sorry, can you repeat it?
Which scheme for code-based and multivariate
You mean
signature?
these ones?
Yeah.
Well, so the ring LW, we tried to look for one of the most efficient ones. I don't remember the names off the top of my head, but it's basically the key exchange. Whatever we have, the key exchange version. And then I think these are the most efficient values that we're able to obtain, looking around through the literature.
So this I'm not sure.
Sorry?
I'm not sure.
Okay, so I can say a little bit more about that. So we got these schemes from an earlier paper, which is cited in our reference list, which contains a comparison of post-quantum authenticated key exchange, protocols, and so we used whatever was in that paper, and so we do have the explicit citations in the corresponding table in our paper.
Yeah, but what is the scheme?
I don't actually remember exactly off the top of my head what they are in each of these cases.
Okay.
So I'm one of the such key exchange paper. So I commented that in our estimation, so ring LW settings is estimated as for encryption scheme. So therefore, it shouldn't be used to a signature scheme, I think. So if you want to use such ring LW scheme, so I think so you are recommended to refer to another ring LW signature schemes to decide the parameters.
I didn't quite fully understand, sorry.
I think the question is that the ring LWE scheme that you described was intended to be used as an encryption scheme. It was not intended to be used for authentication.
Yes.
Right.
And it cannot be used for signature scheme, I think.
Yeah, but the paper that we cited on the post-quantum authenticated key agreement, that paper does use these schemes in the authentication setting.
Yes, but our scheme doesn't use a signature to key exchange.
Yeah, it's not signatures, but it is an authentication step, and it can be, maneuvered into this mold, I guess. Any other questions? Okay, let's thank Vladimir again.